Hello, everyone. Apologies for the delay and for the relocation. There's an issue with the hack room's AV system, but we only have the room until 11 because it's another talk, so we'll try to be speedy. So thanks for coming. Today, Shantanu will be giving a talk. Shantanu joined my research line at the beginning of this year. I don't know exactly when he got here month-wise, but he's been very passionate about electron microscopy for years, and he wanted to share his thoughts about essentially how to get the ultimate resolution electron microscope, covering some of the historical developments and what the current state of the art is like. So yeah, I'll leave the floor to you, Shantanu. And yeah, I'll give you some warnings. Unfortunately, you have to be a bit shorter than expected. It's 10:22. There'll be people coming in at 11.
Okay.
Right. Thank you.
I think, yeah, okay. So I'm from chemical engineering background in my undergraduate work. Then I pursued master's in material science and engineering at Arizona State University, which transformed me into a physics person. So there I earned the interest in the electron microscopy field. So I'll be talking about what are the resolution trends and what is the ultimate resolution, what's the highest possible resolution that we can achieve in transmission electron microscopy. And I'm going to introduce some complex concepts, but I'll just cover a few key points which dictate the resolution limits in the electron microscope. So first, so that's going to be the outline of my talk. And I'll be covering resolution trends, like how the resolution enhancement occurred. And very first electron microscope was no better than the optical microscope, invented by the Ernst Ruska. And then the alignments and the stabilities improved with time, and then they achieved, today we have 0.5 angstrom resolution. And then how aberration correction was achieved after 70 years from the invention of the first electron microscope. And the more problems that we can or we cannot overcome, which decide the true resolution at the end. So here's a disclaimer that I'm not going to talk about advantages or disadvantages of any manufacturers. Then these are the resolution trends. So here's the light microscope, and then the electron microscope. As you can see, the first electron microscope was no better than optical microscope. Then the alignments and the mechanics of the instrument improved, and ultimately now we have the 0.5 angstrom resolution at the end. So first, I would like to talk about this working of the objective lens, because here you can see the specimen. Here is the electron beam, and this is the back focal plane where you get the diffraction pattern. And if you imagine in terms of the wave mechanics, we are bringing all these three beams, the Bragg diffracted beams from the specimen, together on this image plane. So if you imagine in terms of the wave mechanics, you can imagine like it's just a interference pattern that you get on the image plane. So the traditional definition or high school definition of resolution is just what is the minimum resolvable distance between two objects. So as you can see here, this is the image of the traffic taken with the camera, which is defocused a bit. And you can see this circular dots, like spots, these disks, and you know that this is the highest resolution that you can get. You cannot resolve or you cannot obtain an information smaller than the spots. So then the true definition in the microscopy, especially in the electron microscopy, is based on the transfer function, the contrast transfer function. So I'll just explain you what it is. So here you have the contrast transfer. So you can imagine this function in terms of the amplitude. So if you just square this function, you get the intensity. So for example, if you square this function and if you rotate it by 360 degrees and observe from the top, what you get is just the diffraction pattern from an amorphous sample like I have shown here. So, and the spatial frequency means, spatial means it has to do something with space. So it's the distance in the reciprocal space, distance between two objects. So for example, if it is 0.2, you just take the reciprocal of that and then you get 1 nanometer. So this space, this point corresponding to 0.2 is going to be 1 nanometer, means you have the spacing of 1 nanometer between two objects. So we have three definitions of the resolution. So first is the interpretable resolution, which is you adjust the defocus so that you get maximum contrast transfer from here. So you have maximum contrast transfer, and how far you can push to the right side, because as you go on the right side, the spacing is going to get reduced and we are going to increase the resolution. So once you tune the defocus, then wherever you get the first crossover, like where this line cuts the x-axis, that's going to be the optimum resolution with positive value of spherical aberration coefficient. I'm going to introduce what is spherical aberration soon. And this function corresponds to the transmission electron microscope, and this optical transfer function corresponds to scanning transmission electron microscope. And you can see why the phase images or the phase contrast images in the TM are complicated, because you get contrast reversals, and in STEM, especially Z contrast or high angle annular dark field imaging, you have no contrast reversal. So that's the reason why HADF images are very easy and easy to interpret as compared to phase contrast images in TM. So now I'll just show you this slide. So here the resolution of the microscope is 1.24 angstrom. Actually, I'm talking about the interpretable resolution of the microscope, which is 1.24 angstrom. And here the second resolution is the lattice fringe. The third definition of the resolution is lattice fringe resolution. So what happens, for example, here you have this point here, so that's going to be the interpretable resolution. So if you imagine from this point to this point here, but what happens, as I discussed earlier, that you bring all the beams together to interference, and when you interfere these beams together, you bring these two beams, so you get twice the resolution. Sorry. Ah, okay. Yeah, sorry. Thank you. So if you bring these two beams, Bragg diffracted beams together, they will make an interference pattern, and you are able to resolve this 0.62 angstrom lattice fringes. And another definition that I'm going to talk about soon is the instrumental resolution. So I have not shown here, but it's basically a function that comes like this, and it damps as we go to higher spatial frequencies. So it actually never reaches to 0 at this axis, but the point, like the reference is 13.5% of the transfer that we are going to have. So that when this function drops to 1 over e square, or 13.5%, then that's termed as the instrumental resolution. So here in the 80s, so the people were frustrated that how can we achieve the aberration correction, because there are aberrations in the lenses. But so they thought, why not to go to higher voltages? Because as we go to higher voltages, the electron energy increases and the wavelength decreases, so we can expect a better resolution. So here in 80s, this is the image taken by 500 kV electron microscope, and it's the tungsten oxide, and you can see clearly the pentagonal bipyramidal defects, and but still we are not able to resolve the oxygen atoms. So here is an example of mega electron volt electron microscope at Stuttgart. So basically it was developed by Hitachi and JOL. So this is 1.2 mega electron volt electron microscope, and here is the microscope, and above that is the particle accelerator which accelerates electrons to 1.2 MeV. So here is another example. At high voltages in 90s, people finally achieved 1 angstrom resolution. As you can see here, this is contrast transfer function squared, and you can see how far we can go here. It's close to 10. So there in 90s, we finally achieved 1 angstrom resolution. And that's the contrast transfer function, basically is the diffraction pattern from an amorphous sample. So here again, the lattice fringe resolution, if we are getting 1 angstrom resolution, so lattice fringe resolution is obviously going to be as twice as that of the optimum resolution or interpretable resolution. So we can finally resolve this 0.49 or zero point 0.5 angstrom lattice spacings here in the sample of gold. So now going to STEM, as we can see here in my first diagram that I showed here, because the stem lasts long, and obviously you can expect the better resolution in terms of stem. So in stem, basically in the high angle annular dark field, or it's also called as the Z contrast image. So here you can see the CD and TE atomic columns resolved. If you see the line profiles, you can see that they're clearly resolved. So basically, why it's called as high angle annular dark field. So you have a detector, an annular shaped detector, uh, which has a large collection angle. So it collects electrons scattered through a large angles, and you just form a simple image. So you don't have phase information here. So it's just an amplitude image, and that's why these images are quite easy to interpret as compared to high resolution TEM images. So this is the envelope function I was talking about. So if you push that, so it ultimately it's going to damp. This is the phase contrast transfer function. It's going to damp. It's going to bring all the information down at the end. So one way is to enhance the resolution is to push the envelope function. This is called an envelope function, as far as you can. So more you go to the right, you're going to increase your resolution. So this is the conventional. The yellow line is for conventional microscope, and this one, the orange line, is for corrected one, and this red line is for corrected and monochromated. So why this increases, why this improves with the correction, I'm just going to explain soon. So these envelope functions are basically dictated by the chromatic aberrations and the energy spread that you have in your beam. So that's why if you monochromate your beam, then you're going to push it farther to the right. So now there were approaches to aberration correction, and basically Professor Michael O'Keefe from Berkeley lab spent quite a lot of years in enhancing the resolution, and he was among the first person to achieve the sub-angstrom resolution. So people were tired of aberration correction because there were alignment problems. They had theoretical designs, but there were alignment problems and issues. So the aberration correction just failed. So then people tried, we can process the images. So there were two approaches for post-processing. It's the focal series reconstruction and off-axis holography. So I'll just explain in briefly what they are. So in focal series reconstruction, you just acquire the images at different defocus values, and then you reconstruct those images, and you just remove the aberrations by using the software, and then you obtain the aberration free. It's not actually aberration free, but you can say somewhat corrected image. And the off-axis electron holography is simply you have two beams. One beam is passing through your sample, one beam is passing through the vacuum, and you just bring those two beams together to interfere with each other, and then you correct for aberrations. You just apply some phase plate kind of thing, and then you correct for the aberrations, and you have a high resolution image. And online or the direct, they are hardware based. So image correction means if you have a TM, transmission electron microscope, you have a aberration corrector, it is called an image corrector. And if you have STEM, then it's called as probe corrector. So in STEM, I'm using a small fine probe of the electron beam. So I'm interested in getting the probe as small as possible. So in STEM, I'm correcting for the probe, and in TM, I'm correcting for the image. So I'm just correcting the aberrations in the image in terms of TM. So here, what spherical aberration is, first of all. So here you can see this is the lens. It's just conventional optics image, and you have deformities in the lenses. And similarly, you have deformities in the electron lenses that are magnetic lenses. And you can see that this beam is not actually focusing at this same spot as these beams. So all the beams that are farther from the optic axis or making large angle with the optic axis, they are deflected strongly, and then they are not coming to focus on the Gaussian image plane. But so what can be done? So we can just make them less deflected. So how can we do that? So just put a concave lens as shown here. Then these beams are brought to focus. All the beams are brought to focus at the same point. So in this case, the resolution here is dictated by this equation here, 2CS beta cube. And you can see that it is proportional to the cube of the angle. So that's why it's often called as a third order spherical aberration. So now, but in microscope, in electron microscopy, we don't have any diverging lenses. So what we can do, we can use multipole lenses. So because any round lens, like cylindrical lens, is going to focus your beam only, it's not going to diverge the beam. So because the field lines from the magnetic lens are parallel to the electron beam, but in this case you use multipole lenses. So now the field lines, for example, this is north, this is south, and field lines are from here. So you impose a negative spherical aberration effect by using multiple lenses. So in this case, it's hexapole. So, but what happens, they introduce more aberrations in your beam. So when your beam passes through this one hexapole, it's going to be triangle shaped. It's going to be the triangular beam. So now I want a circular beam. So I want to correct those aberration introduced by these multiple lenses. So I put another hexapole with the opposite polarity so that I'm correcting the triangular shape, and ultimately I'm going to obtain a circular diverged electron beam. So here are the first results of the aberration correction. Here is it was the very first time that people achieved, especially Knut Urban and Maximilian Haider, they achieved 1.2 angstrom resolution after putting an aberration corrector. It was just 30 centimeters long. So it increased the length of your microscope by 30 centimeters. And you can see this sample is gallium arsenide with spacing 1.4 angstrom clearly resolved. So this is basically the construction, and this length is the 30 centimeters. So then these are images from Mana's group here. So this image to the left is from corrected. This is from another group from India. But you can see after correction, you have much better quality of the image at atomic resolution. But in terms of uncorrected, you can hardly see the atomic spacings, and you can still have the lattice fringe resolution, but it's not the interpretable resolution, or the information limit is it's not very good. So we can correct for spherical aberrations. We can make CS value to 0, but usually people don't image at 0 CS, because I'll explain later why people don't use CS equal to 0. So people often working with catalysis or the semiconductors, which are oxide semiconductors, and oxides, or people who are dealing with light elements like for CO2 conversion or something like that, they often use negative CS value. So what happens with negative CS value, as you can see, this is the example of strontium titanate with 1,1O projection. And you can resolve this oxygen spacings marked by 1, 2, 3, 4. And they were not only able to resolve the oxygen atoms in presence of the strontium and titanium atoms, but they were able to quantify the defects, the vacancies or oxygen deficiencies there. So in some places you have less intensity, in some places you have bright intensity. So you can actually estimate where the oxygen atoms are missing. Now again, in the STEM, so this hexapole corrector can work with STEM, and it works. COS company has hexapole correctors for STEM as well. But the very first corrector for STEM was based on quadrupole octopole lenses. So here is, it might look complicated, but uh, it's similar to the hexapole lenses. And here is the microscope. It was introduced by Andre Krivanek, who was professor at Arizona State University, and now he is the founder of Neon company. So they have the UltraStem and dedicated scanning transmission electron microscope. So that's the schematic diagram of the stem. And here you have the gun. So usually the dedicated stems have electron gun at the bottom, and you shoot electrons from bottom to top, unlike conventional TMs. So here are the condenser lenses, and here is the corrector, and the rest of the optics is same. So you just place the corrector just after the condenser lens. And this is the first results from the neon microscope, and you can see that this is a gold island on amorphous carbon, and along with, you can observe these small rafts which are monolayers of gold atoms. And if you record the different Fourier transform from different regions, then you get some different information. In some places they are just gold clusters, some places they are crystalline, some places you have single atoms. So this is the image from Mana's group again, and this image is from the India group, Narayan Pradhan's group basically. So here you can see the interface here is very well resolved, but if you zoom into this image, you will hardly see the strain and the distance or the non-uniformity at the interface. So this is the use of aberration correction. This is aberration corrected image taken with Titan. This is uncorrected image taken from JOL 100CX. So it was an accident that people uh, somewhat miscalculated the inner diameter of the annular detector, and somehow they collected a part from the direct beam or unscattered, not unscattered, but the direct beam, which is just on the optic axis. And then they surprised. So this is the example of yttrium hydride, and you can resolve the hydrogen atoms in this sample. And it was the breakthrough, so because yttrium is much heavier than hydrogen, and you can see hydrogen and yttrium at the same time, which is not visible in this bright field stem and this head of stem image. So the advantage of head of stem image is that you are able to image the heavy elements. It's basically useful for imaging the heavy elements, but not the light elements. It's very insensitive with the light elements. And also in terms of signal to noise ratio, head of image has a lot of noise. It's much noisier than as compared to the bright field images, because you have very few electrons that are scattered through large angles. So then I'm talking about chromatic aberration, because you have, if I'm operating a microscope at 200 kilo electron volts, it doesn't necessarily mean that I have all electrons at 200 keV. I have some electrons above 200 keV and some electrons below 200 keV. So that's called as energy spread. And then depending on the energy, if your electron is moving faster, and it's going to be less affected by the lens, and it's going to be focused farther. And if your electrons are having less energy, then they are strongly going to affected by the lens, and they are going to brought to focus before the Gaussian image plane. So this is how the chromatic aberration works. And you can see that it's proportional to beta. So it's the first order kind of aberration, you can say. So it is not affecting the resolution as much as the spherical aberration does. So people were interested in correcting for the spherical aberration at the beginning. Then we have chromatic aberration correctors, just 4 in the world, because the complexity of the building, of the construction, and they're very difficult to align and construct. So people went to so people thought, why not just to remove the electrons which are off energy, which are not at the electron energy that I'm expecting. So that's called as monochromation. So you just filter some electrons off that you don't want, and you get reduced current, of course. And the chromatic aberration is very significant at lower accelerating voltages. So for example, here is the graphene. It's a beam sensitive material. If you go above 60 or 80 kV, then you are just going to burn the graphene down. So in terms of beam sensitive materials like perovskites or MOFs or graphene or other 2D materials, I need to image them at much lower accelerating voltages. So where the chromatic aberration dominates. So then after monochromation at 30 kV, you still have a good resolution. You still have 1 angstrom resolution. It's from Andrei Krivanek, recorded with a neon microscope. So now we still have some things that we cannot correct. So first is the camera readout. You have like the contrast transfer function I discussed about the microscope, which is limiting the resolution. You have the similar transfer function related to the camera readout, related to your detector. But now it's significantly improved because of the invention of the direct electron detectors, which earned the Nobel Prize in 2017. Specifically, Richard Henderson was involved in the development of the direct electron detectors. Then we have electron absorptions. So you have electron beam, then you have some scattered electrons. They may get absorbed in the columns, in the electron microscope components itself. So you lose some electrons and you lose some current, and you increase noise in your image that limits the resolution. Then you have the Johnson quantum noise, which I'm going to talk a bit more detail later. So basically, it's very interesting thing, and people are trying to mitigate this Johnson quantum noise. Then you have dynamic electron diffraction. So you have your specimen. If you have a thicker specimen, then you have electron beam. So it gets Bragg reflected. Then the reflected beam may act as a primary beam for the second atomic plane, and then it gets re-diffracted, and you have multiple scattering within your sample. And that can introduce artifacts that can limit your resolution. So that's the reason in the thicker samples, basically the phase contrast images that you see, or the high resolution TM images that you see, they are not actually what you're seeing. It's not there what you're actually seeing. So then we have tilt angle correction. So if your sample is even tilted by just 1 milliradians, it's going to introduce an error of about 1 picometer. And there are always misalignments. You cannot be very precise, very precise. So if you have non-uniform sample, then your the contrast, the phase contrast transfer function I showed you before. So the contrast that you have is going to be reversed with the thickness of the sample. It's called the Fourier period basically. So at some thickness, you will see the atoms with the bright contrast and the background with the dark contrast. If at some thicknesses, you see atoms black and the background white. So if you have thickness variations within your sample, then the interpretability of your images is going to get bad. So then we have residual lens aberrations. So um, you have objective lens, you have aberration correctors, but the current, the excitation voltage or excitation current that you provide, it can fluctuate. So you have a non-constant or variable current there with some small fluctuations, and that can cause that can influence your resolution. Also, you have electron gun, so voltage fluctuation in the electron gun that can also affect the energy of the electron beam, and then that can introduce more chromatic aberrations and so on. So you have lattice vibrations, you have phonons in your crystal. So the atoms are moving, atoms are vibrating. So imagine you are taking a photograph of a running person or running car. So it will just appear blurred, right? So, and your atoms are vibrating due to the thermal motion because of the temperature. One way is to prevent that is to cool your sample at absolute zero, which is not possible. So ultimately, you cannot overcome this problem. These are limited by the physics, the laws of physics itself. Then you have object point spread. So you have, we have atom, we have protons and neutrons in the atom, we have electrons surrounding the atom. So in the electrons from your beam are going to get influenced by the local charge of the atom, and they're just going to have some spread over there. So that's coming from the electrostatic potential of the atom itself. So that's going to be the ultimate. So you are going to be limited by this object point spread at the end. And finally, the human interpretation. So we should interpret our images correctly. We should know what we are observing. Some manufacturers also do mistakes in terms of estimating the resolution, but it's very important part is the human interpretation factor. So I'll just talk a bit, 2 minutes, about the Johnson quantum noise that I promised. So here is the column, a metallic cylinder, hollow metallic cylinder. So in metals, you have free electrons, you have delocalized electrons, and they are moving, right? So when they are moving, they are generating the currents, and they are generating the magnetic fields, local magnetic fields, nanomagnetic fields. And those magnetic fields are going to affect the electron beam traveling through this component. And then you have some spread over there. So one way to prevent this is to increase the electron column as much as you can, and other way is to cool down the all electron microscope at cryogenic temperatures, because if you heat at normal temperatures, or if you increase the temperature, electrons are going to move wildly. So if you cool them, they are going to get calmed down, so this effect can be mitigated. So I think I'm out of time, so I would like to just acknowledge, I'm just going to my final slide. Just I'll just like to acknowledge um, Professor Peter Crozier from Arizona State University, and Professor David Smith, who taught me the TM course when I was doing masters at Arizona State University. Dr. Peter Ursius and Colin Offers from Berkeley Lab. Uh, I irritated these people a lot by sending a lot of emails about questions and all that, but they never got mad at me. And finally, Professor O'Keefe, not finally, Professor O'Keefe. So he always points out my very small mistakes. Most of his publications are based on the misconceptions that are present in the electron microscopy. For example, how to determine the information limit people use to perform Young's fringe experiment, but then he has a paper saying that Young's fringes are unreliable in determination of the information limit. Rolf Erni from Switzerland, he has a book called Aberration Corrected Imaging in Transmission Electron Microscopy. He also helped me to clear a lot of concepts in aberration correction. And finally, Professor Dr. Giorgio, who put significant efforts in improving my presentation, and he has given some valuable inputs that can be easily understandable to the wide range of the audience and and I would like to thank all my group members. Thank you. Any questions?
Yeah, thank you very much, Shantanu. So it's supposed to be a talk starting at 11 here, but I don't see anyone, so maybe we have time for a couple of quick questions. Do you have any?
You want to see the slide? In terms of the optics, okay. That's a good question.
I'll just repeat for the audience. The question is negative spherical aberration and what's the physical significance?
Yeah. So, yeah. So when you apply a negative CS, so here is the Gaussian image plane. So these beams are somewhat, oh, I'm sorry. Yeah. So this is the Gaussian image plane. And when you put the negative CS value, then these beams with positive CS, which are focusing before the Gaussian image plane, when you have the 0 CS, they are focusing here, but when you have negative CS, they are just going to focus somewhat below the Gaussian image plane. Yeah, yeah, basically, but this Gaussian plane remains constant. When you change the defocus of the objective lens, you're changing this Gaussian image plane, the location of the Gaussian image plane. So it's not exactly focusing, defocusing, but because when you put the corrector, then the Gaussian focus plane or Gaussian image plane of the objective lens stays constant. You are just manipulating these rays which are far from the optic axis or making large angles with the optic axis.
Okay, yeah.
Thanks for the talk. I was just wondering about this last effect you described affecting the
Yeah, Johnson quantum noise.
Yes. How significant it is that there are a lot of
It's not very significant because you have spherical aberration correction and you have chromatic aberration correction, you have monochromations. It's not significant. It's not that significant. But if you really want to push the resolution limits, then if I want a perfect microscope, then I have to deal with it. No, because in electron microscope you have column sets. So if the beam, the electrons that are traveling close to the column. So for example, here you have a circular beam, right? So you don't have a single electron. So some electrons will travel close to the electron column. Some will travel far from the column, like from through the optic axis. So, and you have the lenses, you have objective lens, you have aberration correctors, you have condenser lenses. So you have the metallic components in your microscope that's going to affect the trajectory. Basically, it affects the trajectory of the beam.
Cool. Thank you very much. Maybe we can call it here. Thanks again, Shantanu, for your talk. Thanks everyone
Yeah.
for coming.
And I'd like to say that I couldn't cover a lot of important points and complex concepts, but anyone, if you are having any questions, I'm just around, so just ping me. I'll be happy to talk about it.